All right, recording is rolling. It is Wednesday, December 14th. Posted the rotational dynamics quiz solutions. Those are up there. If you want to do corrections, then you guys got a few days to do those. Right, so want to hit a few things before I get back to the reviewer work. Oh, actually, let's see. All right, so we come from a faculty meeting, and okay, that's right.
Good morning, Great High School. Joshua Houston. Please stand for the pledge of allegiance, fall time on the time.
And resume. All right, so a couple of the main things they told us about is right, so we're about to go into the break, and then when we come back January 5th and 6th, it'll be technically part of our first semester. I don't know if that'll really matter unless your schedule's going to change, but here's the schedule for January 5th. I think what they're going to have us do is stay in first period all day, except for lunch. You'll go to your fifth period, and then you go back to your first period. Okay, and we're going to hit all these topics. So, youth truth survey. Oh, guys, either bring your laptops or some kind of device where you can take the survey, because we've got an hour blocked out for that. Okay, now there's other things we got to talk about there. Okay, and then January 6th is going to be, oh, here we go, more of this type stuff. Okay, so healthy, blah, blah, blah. All right, health type stuff. There we go. Physical health, mental health. Okay, okay. Now, most of you guys are going to be here, but not everybody. So I think I've got 4 10th graders in here. So if you were in 10th grade, there's 4 of you guys, and you guys are going to be relocated to Sean. Is that Mr. Chong, Miss Chong? Does anybody know Sean? Yeah. Okay. I don't know. I don't have a room number for that. So, right. Have to check into that. I just got this a few minutes ago, so no remember this. Okay. But most of you guys are 10 or sorry, 11th or 12th grade. If you're 11th or 12th, you're going to be in here. We'll do that. There are 4 10th graders. You'll go to wherever this is, and I need to find out myself where that's going to be. Okay. All right. So let's put that aside. Do that later. All right. I've been trying to go a little bit faster with you guys compared to my other classes for these conceptual questions. You guys are a little bit faster anyway. I did upload later reviews that did for my other classes to Google Classroom. So if you want to see me slow down a little bit, do a little bit better explanation, draw some of these out a little bit better, that is on Google Classroom. But besides that, actually, I do want to go back and put something I think I did a little bit too fast anyway. Okay. For example, do you guys remember this plane that's flying north, but it's in a crosswind that's blowing straight east? Okay. So its ground speed is faster than its engines can make it go. Of course, kind of going off kind of northeast. You guys remember that one? Okay. And I said, okay, for this particular geometry, it said, oh, okay, well, that would be like a 37-degree angle. Okay. You know what I should have covered with you guys is how do you get it in general, like regardless of what these legs are. Okay. You guys can figure out how to extract this angle, okay, by doing an inverse tan of the ratio of these two. Okay. Or you could do inverse sine ratio of these two or inverse cosine ratio of these two. Right? They'll all tell you the same angle. Right? It happens to be this angle for that particular geometry. Okay, so you guys can extract an angle. Right? You guys can work your way around any right triangle, right? If you have enough information, you can figure out everything about the right triangle. Okay? The other thing is there was a question about like a lantern being held in equilibrium. Okay, so want to make for sure that you guys can do this because I can explain this one a little bit faster yesterday. Right? So the way the problem is set up, they had these very convenient 120-degree, 120-degree, 120-degree angles, right? So everything was perfectly symmetrical. It's like, okay, well, if that weighs 100 newtons, then each of these ropes is pulling with 100 newtons. Okay? But what if the angles weren't so convenient? Okay? Well, you have to break out some trigonometry. You have to say, if you introduce a Cartesian system, that's what these dashed lines are, right? And you break these into components so that they align with the Cartesian system, right? This one's already aligned, so you can leave it alone. Okay? I can say these two conditions here, right? The forces have to sum to 0 along each axis, okay? So the x direction forces cancel out. So this one pulling to the right, this one pulling to the left, right? Those are going to be a wash, okay? That's this condition, okay? This one right here, the 100 newtons down has to match 100 newtons up, okay? Guys, what is the, sort of starting from the answer, what is 100 newtons times cosine of 60 degrees? exactly 50 newtons, right? Because cosine of 60 degrees is exactly 1/2, isn't it? Sine of 30 degrees is also 1/2, right? Sine of 30 degrees for cosine of 60 degrees. Okay. So if you guys saw something like this and the angles were changed, you could do some cosine and sine, and you could do this, right? Right? We do that. There's one more idea I want to make sure you guys can interpret a graph with the situation. So let's go to the edge of a cliff. Right? Edge of a cliff. Okay, I got this ball. I'm going to throw this ball straight up. Give it an initial velocity straight up. Okay, kind of pretty much go straight up and then crash down the valley. So like that. Okay. Let's do just a plain velocity versus time graph for this one. Okay. I know the PowerPoint the other day we did all three graphs: x versus t, v versus t, a versus t. Let's just hone in on v versus t. Velocity could be in meters per second. Time could be in seconds. Velocity does change direction, so better have this one. Okay. Can you guys draw the this graph? We're talking about in the vertical direction, right? So d sub y. Okay. For the scenario, can you guys see that? Let's define down as the positive direction, okay, which means I threw it into negative territory, right? So it's threw it into negative territory. Then you're going to turn around and come back positive, the direction of gravity. Did everybody right now just draw, bam, that right there? Is that what you guys just drew? Okay, so here's your V naught. Okay, all right. Let's interpretation of this. What does the slope of this line tell you? The acceleration, which is free fall gravity in this case, right? It's free fall. How about what does the area of that little triangle right there tell you? Huh? Okay, displacement, and specifically which displacement?
Maximum height.
Maximum height. Yeah, there you go. Okay. From here to here to tell you, right? To call it like H. That's what this is, H. Right? Same thing. Yeah, to the maximum height point. How about let's call this the crash point right here. Here's where it crashes. Bam. A T crash. What does this big triangle tell you? Ah, exactly. Yeah, if you go from here to here, like that height. Maybe I'll call it like H2. How about that? Next could be like H2, right? That's okay. Ooh, how could you find the height of the cliff? Could you guys figure out what that would be?
H2 minus H.
Yeah, this H2 minus this H. That'll do it, right? Right. Take this big triangle, subtract this little triangle. That would tell you what this is. Maybe we'll call it like H3 or something, right? What this? If I guess this whole thing's like H2, right? This little bit here is like H3. Should I color code this or something? Okay. Anyway, do you guys see like a trapezoid here? Did that trapezoid also tell you the height of that cliff? You guys did? Another way to look at it. All right, so a little bit of interpretation there. Okay, so my plan today is to finish these. Probably keep similar pace to yesterday. I'm gonna probably go a little bit faster than my other classes, I think. If you have rotational dynamics type of RQ lined up, I hope to fit in class today. We'll see what we can do. See how the time plays out. And then tomorrow, I do have an FRQ pulled up that involves both, or let's say all three of these units. Right? So there's some projectiles from kinematic motion. There's energy. There's collisions. That's like momentum unit 5. Okay. So that'll definitely have lined up for you guys tomorrow. That'll also help you out with some of the like problem solving multiple choice on the midterm. All right, so see how we can do here. Let's see. We got here yesterday. An object will fall over if its center of gravity is the outside the base of support. Okay. So an object thrown into the air will spin about its about the center of mass or center of gravity could be good. Right. Center of mass, center of gravity. A picture hangs from a wall on wire passed over supporting nail. The picture is in the yeah. Go back to what?
An object will
fall over if its center of gravity is outside the base of support. Okay. So here I got some pictures here. Okay. Suppose you have a floor. Here, let's get a big old floor going. what if you have like a pyramid shape, right? And center mass is right there, and here's the base of support. Right? See how the center mass is over the base of support, right? So that's pretty stable. Okay. But what if you invert that pyramid? Okay. So center mass there, right? Now, if it's right above base support, okay, right, that's a really tenuous situation. Okay? But if you tip it a little bit, boink, okay, then anytime, here, let me show you guys something that's definitely unstable. Okay, what if you had something like this? Here's the center mass, here's the base of support, right? See how the center mass is not over the base of support? So is this whole thing gonna have a torque, rotate clockwise? Right? So that would be unstable, right? Right? Something like that. Got a picture hanging on a wall from wire passed over supporting nail. The picture is in equilibrium, stable equilibrium. Okay. There might be multiple good explanations for this. Here's the center mass of the whole picture frame. Okay, here's the supporting nail. Here's the wire. Okay. Would you guys say that the center mass is directly beneath the support? Yeah, right. So that would be the place that would be stable equilibrium. Okay. What about this? What if you give this a little push and it rotates a little bit? It like rotates like this, right? Like center mass could like rotate along the circle around the supporting knot, right? Would it just want to drift back and then go back to the original place it was, right? Is the center mass the lowest place it could ever be? That's like the ball wants to roll at the bottom of the valley, something like that. So I think all this would be true, right? All different perspectives of why it would be in stable equilibrium. Torque. Oh, is torque R cross F? Right? Radial arm crossed with the force, turning a wrench, opening a door. Suppose you try loosening a nut with a wrench and the nut doesn't give it all. You increase your chance of success if I'm thinking of three things. You can push as hard as you can push on the wrench. You can also do what two things?
Lengthen the wrench?
Yeah, make the wrench longer or apply the force at the complete end of the wrench, increase that the radial arm. Right. And the third thing you can do swallows a cross product. Make sure those two vectors, the radial arm and the force, are what to each other? Perpendicular, right? Perpendicular, right? So sine of 90 degrees, you can get 100% of the torque, right? RF sine theta. The resistance an object has to changes in its rotational state of motion. Ooh, that's called what? Rotational inertia, right? So resistance to change in motion. You guys remember those 2 meter sticks had same masses but taped at different locations? They were easier or harder to shake back and forth, different rotational inertias. Suppose a huge rotating cloud of particles in space gravitates together to form a dense ball. As the cloud shrinks in size, is it going to spin faster, just like this ice skater? Right? It gravitates closer together, it's rotating, spin really fast, right? It's conservation of angular momentum going on right there, right? A ring and a disc roll down a hill together. Which reaches the bottom first? Here's the ring. Here's the disc. Is the disc always going to beat the ring? Yeah, right. Newton had the original insight to see. So these questions are like mostly in order how we did the class, but there's a little bit out of place. Okay. Newton had the original insight to see that
It's 2B versus 3B.
okay. I remember the multiple choice on looking at the moon, looking at the apple fall from the tree. Right? Was Newton the first person to notice that the moon was orbiting the Earth? No, right? People knew that. Right? Was the first person to see that the one side of the moon always faces the Earth? It's like tidally locked. No, people always knew that. Right? Was he the first person to realize that the apple falling from the tree and the moon orbiting the Earth were part of the same phenomenon? Yeah, that's what he was the first person to realize. Right? Some kind of gravitational attraction. Newton reasoned that the gravitational attraction between the Earth and the moon must be, well, here's what Newton came up with. F equals G(m)(m) over distance squared. Okay. So I bet this gravitational force is proportional to each mass of the Earth, mass of the moon, and also inversely proportional to the square of the distance between them, right? If you know this, right, this is the Newtonian gravitation. If the radius of Earth decreased with no change in mass, what would happen to your weight? Okay. So, standing surface of Earth. Okay. Here's the radial size of Earth. Maybe we'll call it capital R. Okay. Let's go. Here's your mass. Here's the mass of the Earth. Okay. So your weight, which is a force, is universal gravity constant, mass of Earth, mass of you divided by the radial size of Earth squared. Okay. So what if we like crunch down the Earth? So its mass isn't changing, right? But we're just like squeezing it like to a little dense ball. Right? So you wouldn't actually be getting physically closer to its center, wouldn't you? Okay. So let's see, that's the same, that's the same, that's the same. Nothing in the numerator changes, but the denominator gets smaller. Ooh, that's what happens when you divide by smaller numbers. What happens to the fraction? It's bigger. Ah, so what's happening to your weight? Staying on scale? Increasing. You're getting heavier, right? You're getting heavier. Right? By doing nothing but squeezing down the Earth, you're getting heavier. Standing on the surface. Suppose the gravity force between two massive spheres is 100 newtons, and we're going to double the distance between those two. Okay? We can still use the same formula. Okay? So, got two asteroids floating around. If you throw a factor 2 in that distance, then what happens to the force?
1/4.
1/4. Yeah, 1/4 of the force. Okay? So, if the old force was 100 newtons, what's the new force? 25. Yeah, 25 newtons. Right? Double the distance, a quarter of the force. By noticing Uranus's orbit is perturbed and by using the law of gravitation, two astronomers independently discovered. Okay, this is a fun trivia story. The answer to this is Pluto. Hold on, no, actually, let's go with Neptune. Right? Both are true, right? Neptune and Pluto, but saw anything like that. Both those were discovered mathematically before they were ever seen through a telescope. Okay? Some people were looking at these orbits saying, oh, hey, they don't follow exactly what Newton and Kepler said they should do. So where would some mass have to be such that it caused this particular perturbation? Oh, hey, look, it's Neptune. Okay? And then later on, oh, hey, look, it's Pluto. The force of gravity is greatest on you when you are standing. You guys remember we did planet surface. If you tunnel down into the center, say a spiral staircase, right, versus if you take off in a rocket. Right. What is your weight in relation to, say, okay, some general size, lowercase r, and let's go capital R for the fixed radial size of the planet. Okay. So put some general r here. Here's the surface of the planet right here. Okay. What is your weight? What's your weight right in the middle of the planet? 0. Okay. And your weight on the surface is some value, right? Is there a linear relationship from one to the other? Yeah. Okay. And part of the proof involves, you guys remember the whole thing about like if you're in a spherical shell, there's gravity-free interior. Okay. It's like this guy halfway down. Okay. You can basically ignore everything above him in elevation and treat it as a series of shells. Okay. And so it's like as if there's just one tiny planet below him. Right? Anyway, you run the math, and it's a pretty much linear relationship. This guy kicking off in a rocket. Is there an inverse square relationship between the gravity pull of the Earth and him? So where do you weigh the most? Boom, right here on the surface. You'll lose weight either tunneling down or taking off in a rocket. The reason the moon does not fall into Earth is, do you think it has sufficient tangential speed to fly around the Earth? Okay. You said gravity force equal to centripetal force. You get the orbital speed for a circular orbit is square root gm over r. Right. So I'm thinking as long as it has sufficient tangential speed, right, then it will never fall into the Earth. As long as it's moving fast enough to the side. According to Newton's laws, a rock and a pebble will fall with the same acceleration. So that would I don't remember where they're going with the multiple choice for this one. Right? I mean, that would be true, right? It's in a maybe the same gravity field, right? So the rock and the pebble have different weights, but they also have different masses, and those two effects cancel out. So it's a version of Newton's second law of motion, right? Weight divided by mass, right? But it's for free fall. It's like that. So in the same gravity field, they would have the same acceleration. Okay. The value of acceleration due to gravity, lowercase g, okay, isn't that gm/r²? Okay. So it depends on the universal gravitational constant. It depends on the mass of the planet. It depends on the radial size of the planet. Right? All those things matter. Right? Okay. And if you plug in the numbers for Earth, you get 9.8 meters per second squared. Right? So, the gravity field strength at the center of the Earth. Oh, well, you guys just told me that's 0. Right? So every grain of sand on Earth pulls you a different direction. All zeros up. If you were to weigh yourself in an elevator that is in free fall compared to your ordinary weight, you would weigh, well, if it's in pure free fall, what is your apparent weight? 0, right? 0. But you just be floating around like an astronaut. If it's anything that's accelerating down, you would weigh less than your usual weight. If it's accelerating up, you would, you're talking about apparent weight or maybe the normal force from the scale that you're standing on. If it's accelerating up, you would appear to weigh more. Right? Earth's gravity pulls on you saying there was we talked about elevator physics, right? Through all that. A black hole is an object that is maybe so dense that not even light can escape it. If the sun were to form to collapse into a black hole, which it physically can, it doesn't have enough mass, but just make believe. Right? What would the Earth do? Right? Well, from the point of view of universal gravitation, mass of the sun, mass of the Earth, distance between the Earth and the sun squared, right? Something like that. Okay. Right. Here's 1, here's the Earth going around. Right. Let's see what changes. Universal gravity doesn't change. Mass of the sun, now black hole, that's whatever it is. Right. The mass of the Earth is the same. The distance between the two is the same. So is everything the same? I think bit by bit, everything's the same. Right? So would the Earth just continue to orbit just as it is now? Yeah, according to this, it would. The Earth just orbit the black hole. When a star collapses to form a black hole, that happens to its mass. Well, its mass is conserved. Right? It doesn't increase mass due to the collapse. Right? It gets more dense. It gets less volume and more density, but mass is conserved. Early bird communication satellite hovers over the same point on Earth indefinitely. Why? So here's the Earth. There's like a satellite. There's a particular orbital level. It's definitely not low Earth orbit. Low Earth orbit takes about 90 minutes to go around the Earth. Okay? Orbital speed, circumference of the Earth, blah, blah, blah. Right? The moon, way out here, takes like 28 days to go around. Okay? Well, there is one place where it takes exactly 24 hours to go around. That's the answer to the question. If it takes 24 hours to go around, okay, so you're just like standing here on the equator, look up in the sky, it's like, hey, it looks like it's just hovering on the same point in the sky all day, just over us. How's that? Oh, because it's rotating with the Earth, right? 24 hours orbital period. If you have a 24-hour orbital period, going straight east. Compared to the period of a satellite in orbit close to Earth, the period of satellite orbit far away from Earth, it wouldn't be a longer time period. So low Earth orbit's about 90 minutes. You can go up higher up and get to 24 hours. You go further still and get to the moon. It's like 28 days. Oh, where does a satellite in an elliptical orbit have the greatest energy? Sorry, kinetic energy. So have like planet, maybe like an elliptical orbit, maybe it's a sun and a comet, right? Something like that. Something that's pretty elliptical going on right there, right? Let's do the full version of this. So mechanical energy could be potential energy plus kinetic energy. Okay? Now this point right here, this perihelion, it's a comet going around the sun called the perihelion. There could be a lot of what kind of energy? A lot of potential and only a little bit of kinetic that's going around real slow. Okay? Versus over here, there's a lot of what? a lot of kinetic and only a little bit of potential. Right? But what if you add these two together? Is the total mechanical energy constant all the way around? Yeah, the total is constant. Right? The potential plus kinetic is constant. Right? I think I remember there being an AP question in the past where they asked this, but they did one more thing, which is if you look at the universal form of gravitational potential energy, remember it's always negative, right? So I think there was some bar charts, and you had to realize that, oh, well, this is always negative, and it's like one more twist. But yeah, the sum is always the same, okay? And in this case, with like -3 units of potential energy be more than -7 units of potential energy, something like that. Let me draw that up with you guys, because this one takes some deep thinking, and there's a small chance that you might have something like this. Okay. Let's do or what did I just call these things? Sorry, this is going to be the aphelion. This would be the perihelion here. Oops, got this terms backwards. So when it's close to the sun, when it's far away from the sun, let's do some energy charts for this. Attention here. Okay. So we're looking at how much energy, okay, and we'll go kinetic. Go negative with this too. Let's go kinetic, potential, and total. Kinetic, potential, and total. Okay. So on the far side, there would be a lot of potential energy, but remember, potential energy is always negative, so it might be like a negative value there. Okay. Here, there's not very much potential, or I could say a lot more negative potential, something like that, right? Okay. Or like this. Okay. Over here, there's a lot of kinetic, and over here, there's only a little bit of kinetic. So there's a lot of kinetic versus just a little bit of kinetic. Right? And then the total energy, I think anything is like orbiting, technically have negative total mechanical energy, like around that system. So something like that. It's some weird chart, right? That didn't change. So it's the same for both. Right. So no, it's weird just because one of them goes negative. But, where does a satellite in elliptical orbit have greatest kinetic energy? Well, that would be the point where it's closest. Okay. What remains constant for a satellite in an elliptical orbit? You can say the total energy remains constant. Right? Potential and kinetic individually change, but the total energy, if you add them up, it's the same. All right, and then we got a round of questions here at the end from all different sections. Acceleration is defined as a change in what? Oh, yeah.
So is the total kinetic and total energy same as mechanical energy?
Yeah. Total energy, mechanical energy. We're going to take those to be the same. Okay, so that's that list of options. We have kinetic energy, potential energy, spring potential or gravitational potential. Yeah, so those forms. Okay. We don't really care about in this class things like chemical energy or energy stored in a battery or anything like that. Okay. Thermal energy, we're going to ignore. Okay. So would acceleration be a rate change of velocity? Right, change of velocity for a change in time. Okay. So a change of velocity per unit time. The acceleration produced by a net force on an object. Acceleration is the net force acting on a mass, right? So I'd say it's directly proportional to the net force acting on the object, and also inversely proportional to the mass. Is the direction of the acceleration the same as the direction of the net force? Yeah, that's also true, right? Think about vector quantities, right? Directions are the same. Two gliders, same mass and same speed, move toward each other on the air track and stick together. After the collision, the velocity of the gliders is okay. What section would you think to use as a framework to answer this? Yeah, momentum. Yeah, because there's a collision going on. Okay. I said same mass and same speed, opposite direction. So glider, okay. Same mass, same speed, opposite direction. B, yeah, pow, right there. Okay. And then they stick together. So what's the final velocity? 0, right? So we have equal and opposite momentum. So there's zero momentum in the system before and after because they're vectors, right? So it's like positive 3 units, negative 3 units. Perfectly inelastic. Yeah, so quite stick, perfectly inelastic. The machine puts out 100 watts of power for every 1,000 watts input. And now if that was a continuous process, or so you're putting in 1,000 watts, and let's say there's like some heat loss, it heats up, blah, 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 right? It's like vibrating, but then you get 100 watts of useful power, right? What would be the efficiency? You do 100 over 1,000, get like 10%. Is it like 10%? Potential energy is an energy an object has because of its, could you say like height or location? Those would be good options, right? Some kind of height or location. As the rotational speed of a space habitat increases, the apparent weight of the people inside. When they talk about O'Neill cylinder. Right? So there's a central axis that it's spinning around. Okay, there's a ladder going across the middle, just for out of this picture. Okay. Got a bunch of people standing inside here. Okay. If it's big enough, it's rotating at the right speed, they might think they're like on a planet. Okay. There's no real gravity, but there's artificial gravity. It might be kind of hard to tell the difference. It's big enough. Right? Let's speed this up, spin. What's a good equation to tell them the artificial gravity that they feel? Oh, yeah, v squared over r works. I like omega squared times r for O'Neill cylinder, but either one of those, right? Right. So, but either one you use, if you're speeding up spinning, do they feel heavier and heavier? Like there's more artificial gravity. You're gonna feel really heavy, right? It's like a centrifuge, like feel super heavy. If it's not spinning at all, they would feel zero artificial gravity. Float around. All right. So, you guys good with these conceptual questions? Then? That's okay. All right. So we've got about 15 minutes today, and then tomorrow to fit in a couple of last FRQs, and I'll put those in grade books, and those are only going to boost your grades. Okay. So let me get that to you guys, and you know what? Here's what I'm thinking. Probably I'll have you guys do the FRQ today. You guys can hold on to it, and then tomorrow we'll go over the scoring rubric, and then we'll do one more, right? And then that'll take us to Friday. Friday is like a 20-minute class.